Welcome everyone, and I wanted first to welcome prospective students who are joining us today, and we very much hope to leave a good impression on them. We are trying to do our best to attract them here in the next academic year. We just heard a very interesting ITC colloquium by Dana Anderson, and she will tell us some more about protoplanetary disks, which obviously are the birthplaces of planets like the Earth, and that's why we care about them. It's sort of like the crib led to our existence, and Dana is observing or doing theoretical calculations that would help interpret observations of those with ALMA. So we will hear more about investigating the chemical evolution of protoplanetary disks in a few minutes. The other speakers today are Antranik Sefilian from University of Arizona. Here you are. Who will tell us about planet-induced structures in debris disks and the role of disk gravity. We will also hear from Yoav Zigdon from the University of Cambridge in England, who will tell us about the ensemble average of black hole Mimickers, and that's more in the context of particle physics. And then finally we'll hear from Daichi Hiramatsu from the Center for Astrophysics over there, who will tell us about uniform characterization of interacting supernovae. But before we start, I first wanted to say everyone is well aware of the uncertainties of the future, and we got a lot of messages from leaders of Harvard University, including the president and the dean of the Faculty of Arts and Sciences. So we will wait to see. Maybe they know more about the risks of the future. So a lot of people are worried about it. It will obviously affect at least the Harvard component at the Center for Astrophysics, but we still have to wait to see exactly the ramifications for the future. But if you check the news, I mean, you all very naturally get depressed by these news, but there was one bright light this week. A couple of weeks ago on Tuesday, SphereX was launched successfully, and I sent an email this morning to Gary Melnick, who is one of the leaders, PIs of this instrument. I just asked him to give us a brief overview in a few minutes about SphereX before we start with the program. Please.
I'll stand so it's a little bit easier.
Or you can go there if you want.
Okay, I think my voice projects pretty well. So yes, as Avi said, after several delays that were like an emotional roller coaster, we got off to a picture-perfect launch and insertion into exactly the orbit we wanted, which was a sun-synchronous orbit, which is important insofar as what the mission will do is obtain spectra of every 6 by 6 arcsecond point on the sky for 4 pi steradians. And we will do this 4 times during our baseline 2-year mission. The primary scientific goals of the mission are threefold, though I'll hasten to add that the ancillary science, if you have spectra of every position on the sky between 0.75 and 5 microns, there are hundreds of projects that can be done with that. But the design was driven by 3 scientific goals. One is to look for or to set tighter constraints on a quantity called non-Gaussianity, which relates to constraining the physics of inflation. In short term, the smaller the non-Gaussianity is, the more it informs us about the number of fields that might have contributed to putting the bang in the Big Bang. A second goal is to do total intensity mapping in order to set constraints on the epoch of reionization. The way that we will take data in our sun-synchronous orbit. We will sweep through the whole sky, every orbit, a slice of the sky. When we cross the galactic plane, we will undertake the third objective of the mission, which is one that we're leading here, which is to use known background stars against which we will do absorption spectroscopy. And in this wavelength range lie some very prominent ice absorption features due to water, CO2, and CO, among several other weaker features. But we expect to obtain signal to noises between 50 and 100 on every one of these 10 million lines of sight that we intend to probe. When we sweep past the galactic plane, out of the realm of the ices, we will do the cosmology. We will look at and obtain the redshift, we hope, of more than 300 million galaxies in order to constrain inflation. And when we're at the poles of our orbit, which we cross every orbit, so we go particularly deep, we'll do the total intensity mapping to constrain the epoch of reionization. Lastly, the baseline mission is 2 years, again, 4 complete sky surveys, and the data will all be made public. So any project you can think of that benefits from a spectrum between 0.75 and 5 microns, come to us.
So Gary, if you had to forecast, what will the Nobel Prize be for? What would you?
I'm a poor forecaster of Nobel Prizes. I guess it's whichever. I mean, if this rises to that level, whichever evokes the biggest surprises.
Right.
And you know, the Nobel Committee is a mystery to me, so I don't know what their proclivities are.
Well, these days they give it to AI.
But last, I'll just close by saying that, again, I owe a debt of gratitude to Charles because he approved the initial funds that allowed this to get rolling.
Thank you, Charles. Obviously, we'll hear updates when there are major discoveries.
Yeah, I should just add, with that regard, the on-orbit checkout is about 5 weeks, after which we'll start to get data.
Excellent. We'll be patient. Okay, so let's start with Dana.
All right. So I will be talking to you today about investigating the chemical evolution of protoplanetary disks with this question of, do we expect the birth order to affect the composition of giant planets? So ones that form earlier versus later. So we're interested in protoplanetary disks because they are the birthplace of planets. The gaseous composition of the disk, which makes up most of the disk, will contribute to the primary atmospheres of giant planets, whereas the dust component contributes to forming planetary cores and rocky or terrestrial planets and minor bodies like comets and asteroids in our own solar system. And within this, I'm mostly interested in what's happening to the volatiles, oxygen, carbon, and nitrogen species, which these elements make up a very small portion of the total mass of the disk, and they're divided between the gas and the ice phases, depending on where you are in the disk and the disk temperature. And our goal is to be able to link the protoplanetary conditions to different planet formation pathways and different planetary outcomes. So in order to understand why we use chemistry in order to study these disks, it's important to recognize that within a protoplanetary disk, here I'm showing a vertical slice through the disk, we have these gradients in environmental structure. So the density, we have much higher densities in towards the center, inner disk towards the star, and in the middle of the disk, decreasing out towards the surfaces. And temperature, we have warmer temperatures closer to the star and in the irradiated surfaces, and cooler temperatures in the shielded region in the middle of the disk. And all of these conditions lead to a variety of different chemical regions throughout the disk. So we have both vertical structure, the irradiation, breaking down molecules into ions and atoms, and then radial structure. As you go further out from the central star, we're getting into cooler regions of the disk, and some of your disk materials are freezing out into ices, changing the composition of potential planet-forming materials. So depending on where you form in the disk, you're scooping up material around you that the solid and gas has different compositions that are eventually going to affect the composition of your planet. So one other consideration is that when we're looking at this picture, we're just thinking about a single snapshot in time. Whereas in reality, we have a variety of different processes occurring over time, including dynamics, the motion and mixing of materials in the disk, different chemical processes occurring over different timescales, and even evolution of the star and the environment that can change the picture of the chemical composition and what materials are picked up by different planets as time goes on. And so this brings me to my question of, does birth order affect giant planet sizes and compositions? Because maybe the planets that form earlier are going to have a different environment in terms of total solid to gas mass in the disk, as well as different chemical composition, and end up with a different size and composition compared to later generations of planet formation that form after the disk has evolved, lost some of its mass, and potentially changed the chemical composition of its gas and solids. But in order to answer this question, we have to study the evolution of protoplanetary disks. This has been done for the solid materials in the disk. So this is looking at the dust mass in the disk over regions of different ages. So each of these colors is representing a whole population of disks in a star-forming region of increasing ages. The dots are presenting smaller samples or single sources. And we can see here that as we go from the younger disks to older ones, there is a noticeable drop in the total amount of solid material as a sign of evolution of the solids. But when it comes to the gases, we still don't have this understanding quite yet, because we need more observations in order to probe the evolution of this gas. When we only have one gas tracer, for example, CO, that can tell us about the amount of CO that's in the disk. But we really need the power of having multimolecular observations where we have multiple molecules in order to really constrain gas masses, chemistry, and other properties of the disk. In particular, I'm interested in using this combination of molecules, N2H plus and CO, because for the question of evolution, we can actually distinguish between chemical and mass evolution of the disk. So as the disk is evolving, if the CO relative to molecular hydrogen abundance, so the chemistry in the disk is changing, we could see a drop in CO fluxes. But we could also see this if we're just losing overall mass in the disk. So if our H2 in the disk is depleting over time as it's evolving into a mature planetary system like our solar system, we're losing that gas, we're going to see the drop in CO. But when you add N2H plus to the equation, we see that in the CO depletion case, N2H plus actually increases. And this is because a chemical relationship between N2H plus and CO, where CO is one of the main destruction pathways of N2H plus. So when the CO is disappearing from the gas, then the N2H plus is going to be enhanced. So then we can distinguish this CO depletion case from the mass depletion case, because as we're depleting the mass in the disk, all of the molecules are going to be decreasing, both the CO and the N2H plus. So in our early observations, we compared the N2H plus to CO flux ratio. So here I'm showing for CO, this is C18O, a rare isotopolog of CO, tracking closer to the total molecular column density. Here I'm looking at a range of protoplanetary disks. The orange ones are around higher mass stars, so we'll ignore those for the purposes of this talk. We're interested in the lower mass T-Tauri stars, the disks around these sources, and these are in the blue points. And you can see I've sorted them in increasing age towards the right. And you can see that the older disks tend to have higher N2H plus over CO ratios than the younger ones. But this is just a hint of a trend. We don't have a lot of data there. So we're going to increase to a slightly larger sample. We were able to compile this sample of 20 sources that all had these molecular tracers, including our N2H plus to CO. And we found across this sample, when we compare the fluxes of all 4 molecules, a lot of diversity. So even if we look in a single region, for example, in this lupus region shown in green, we have some disks with a much higher amount of CO relative to the fluxes of other molecules. And then we have some disks that have N2H plus much greater than the CO. So even within a single star-forming region of a single age, we're seeing a lot of chemical diversity. And if we go back specifically to the N2H plus over CO flux ratio that I was mentioning before, and look at this versus age, again, of the different star-forming regions that the disks are coming from, we can see that our trend, while we still have the older disks sort of appearing higher relative to the younger disks, this trend does break down a little bit. We have this young disk in lupus that has a similar N2H plus to CO ratio as some of the old disks. We have this one here, which is just an upper limit and could be some lower level. So we're seeing that there isn't a direct trend with age. We have a lot of diversity within these regions. But again, this is a very small sample. And so what we really need is a large uniform disk survey that has more equal numbers between our different regions, and we can really get a statistical sense for these trends. So that brings us to the ALMA-DECO large program. This is going to characterize the mass and chemistry of the gases in young disks. So this is focusing on disks that are in the 1 to 3 million year range in 4 different star-forming regions shown in the plot here. It's going to get a total of 80 disks, so 20 per each of the 4 regions, and it surveys a range of different stellar masses as well as disk sizes. So I'm showing here the dust mass, and then the size of the circles are representing the dust radius of the disk. So we're getting a sample of larger, more extended disks compared to the compact disks, different stellar types from K to M star across the 4 different regions, and a whole suite of different molecular tracers, including the N2H plus to CO, to tease out this chemical depletion versus mass depletion question. So with this large survey, we're really going to be able to get a handle on what's happening in the young disk sample, and whether that's uniform across the young disks or dependent on different environments and the stellar or disk properties. But then to bring back that question of evolution, we're adding on this follow-up survey that's been completed, which focuses on the elder disks in that upper SCO region, which is greater than 5 million years old. So representing this older range of protoplanetary disks. And we've done the same style sample that we had in DECO. So we have 20 disks in upper SCO. We have a similar range of stellar host masses and the same molecular line emission tracers. And so we're going to be able to compare between our older disks and the DECO sample our estimated gas masses and gas compositions from the same tracers. So that brings me to my conclusion that disk evolution is expected to affect the mass and composition of the disk, and potentially the composition of planets will be dependent on when the planets form in the disk. And to really understand how much of an effect this has, we need these large surveys focused on disk populations of different ages. All right, thank you very much.
The survival of N2H plus must also depend on the electron fraction, because you can get an electron attached and then you lose that. So that depends obviously on the X-ray illumination, all kinds of flare activity and so forth. How do you model this?
So that's always, you saw my previous talk about the model comparison. The electron abundance is a question that comes up all the time. The codes each handle it a little bit differently. It's usually part of the chemical network that we have a lot of chemical reactions that produce electrons or neutralize atoms with that electron. So it's just part of the chemical network, and we predict it. But yeah, how it's treated within the chemistry does depend on the different assumptions people make about their networks.
Thank you. Gary, and then please.
Something of an advertisement both for your talk and for students who are interested in this. We were just awarded another NASA mission that will look at protoplanetary disks with very high spectral resolving power in order to do line tomography in the ground state and first excited state of HD, so that we should be able to work around this problem. We can get at the mass of the gas directly. We'll also do the same tomography to get the radial distribution of gas phase water in the disk as well. So
there is nothing that the theorist likes more than data. Real theory.
Nothing an observer likes more than getting awarded missions. We're all happy.
Yeah, thank you. I've been really impressed by a lot of the new ALMA data that shows these interactions between very young forming stars, and that changes the chemistry in their disk. And I'm wondering if these are too old to be affected by that, or if some of the chemical variability we could see has to do with the environment of these things, and if they're still included.
So there have been, in the DECO sample, it's this one, the DECO sample, the younger sources, there are some that are interacting with their environment. And we have a large team of collaborators, and there's a group of them that are focused on these environmental reactions. But what effect that has on the chemistry, we don't know yet, because we haven't derived all the C to O ratios yet. But that will be interesting, how much that actually plays an impact on affecting the mass and chemistry evolution.
Last question, anyone? If not, let's thank Dana again.
That. Okay. Cool. Hi everyone. Thanks for being here. I'm Antranik Sefilian. I'm currently a 51 Peggle AB fellow at the University of Arizona, and today I wanted to talk about some recent work I've been doing with some colleagues on the vertical structures of debris disks. To start off with, what are debris disks? They are basically the analogous versions of the asteroid and the Kuiper belt, which exist around other main sequence stars. And they are pretty much common. You can find them around about 1/3 of main sequence stars in the solar neighborhood. And what is interesting is that some of them do appear to be structured, like you can see in this gallery of images from a recent large ALMA program called ARCS. And if you just take a brief look, you can see that some of them are narrow and eccentric, and some others are actually wide radially and have substructures like gaps, warps, and spirals. And I guess, motivated by solar system studies, the idea is that these structures are thought to be carved by planets. And what drives theorists in the field is that if we understand how planets carve structures, then we can do the inverse problem and use structures to infer the presence of planets in such systems. So that's the brief, quick motivation on why to study debris disks. And we've been doing this for some time, maybe 2 or 3 decades now, and humans are generally smart. So we've come up with pretty much all answers about how to imprint structures in debris disks, and the title gives it away. We think that planets can actually produce most, if not all, of the observed structures in debris disks. So whether that's the location of the inner edge of the disk, right. Whether that's the location of the inner edge of the disk, or gaps, or eccentric structures, vertical warps, which I will focus on in this talk, spirals, and so on. So we think that all of these structures can be explained by planets. And if we now take all of the predictions of planets and put them in a plot, we get this figure, where I'm showing the planet mass as a function of same major axis. The black dots are actually planets that we've detected, right? And the color points are all the predictions that we have, or at least almost all of them. They have some cool features, right? You can see that they all lie about, at tens of AUs, tens to hundreds of AUs, and they vary in masses anywhere from, a few Neptune mass to a few Jupiter mass. And the hope is that, some of these, this is just a crude limit of what JWST can detect, but the hope is that in the coming years, or maybe even sooner than that, I don't know, JWST should be starting to detect more and more planets that we think exist in such debris disk structures. I also have to add that, I guess, if I'm not mistaken, the only apparent success of this story of ascribing structures to planets is the story of Beta Peak, right? Beta Peak was first observed in the 80s. We first saw the warped structure in its debris disk, and then theorists thought, great, this should be sculpted by a planet on an inclined orbit, and such a planet was actually discovered after the prediction by a decade or so in 2010, and this is what the animation is showing. It's just showing the direct imaging results of the planet that we think is responsible for sculpting the warp in the debris disk. And apart from this, I'm not aware of any other successful prediction or ascribing structures to planets. But of course, our predictions, I think, are as good as our models are. And this brings me to the point that I think is a critical gap in our modeling efforts theoretically, and that has to do with the effects of the disk gravity itself. So what I mean by that is almost all models, of course, account for the effect of the hypothetical planet that we invoke by hand on the distribution of planetesimals in the debris disk, but they almost all neglect the back reaction effects of the planetesimals on the planet, and most certainly they ignore the self-gravitational effects, like the interactions between the planetesimals themselves, okay? So in other words, theories are basically assuming that the debris disks are massless, and we know observationally that they should have some mass, whether that's few Earth masses or maybe tens or hundreds of Earth masses. So I've been, doing this business for a couple of years now in coplanar setups, which I will not talk about, just show the image, and if you have questions, I'm happy to answer. But today I'll be talking about what I've been doing in the last couple of months, focusing on the vertical aspect of the dynamics. So just so we are on the same page, what I'm assuming is this. I have a single star. It is orbited by a planet which I invoke by hand. It's on an inclined orbit initially. And there's a disk exterior to the planet, which is initially razor thin, no structure within it. But I will ascribe some mass to the disk and study the effects that comes after because of accounting for the effect of the disk mass. I'm not doing, I like my paper and pen, so to keep things simple and analytical, what I'm doing is I'm accounting for the effect of the planet on the disk and also accounting for the back reaction of the disk on the planet. This keeps everything analytical and nice, but I'm not accounting for the self-gravity of the disk itself, okay? If I do this, then I will get such images. It's a bit complicated and not the complete story, but what I'm trying to show is if we start with the same planet and the same disk, right, and we just pump up the value of disk mass as we go from left to right. So this is a massless disk. This is a disk which is less massive than the planet, and then the disk is more massive than the planet on the third column here, and time goes down. Okay, so initially they kind of look similar. You get some vertical warp structure to begin with. But ultimately, the disks settle actually into completely different configurations and architectures depending on the disk-to-planet mass ratio, right? So here you see that it's kind of uniform, a boxy structure which is in the same plane as the planet at that time. Whereas if the disk is less massive than the planet, then you kind of get this localized broken disk structure or maybe a warp-like structure depending on the PSF and so on. And if the disk is much more massive than the planet, then the disk actually does nothing. It just actually does something. It remains rigid to perturbations from the planet and prefers to stay thin, and that's why you cannot see much of stuff towards the larger radii. There are many other implications for what it means for scale heights, how we explain warps, and so on, which I will not discuss. But I will be giving another talk tomorrow at the CFA disk group meeting where I will be going much in depth about this, so you're welcome to attend that. Just as quick implications for all of this business now with the disk mass, this is some system, HD 110058. It's been imaged to show some warp structure. And what I'm showing here is basically the predictions for the planet. This is the planet mass as a function of its major axis. The colored regions are shaded out for different dynamical reasons, which I will not go into. But what I'm trying to highlight is now the difference for the predictions of the planet if one uses a massless disk model or a massive disk model. Okay, if you use a massless disk model, as commonly is done, you will get this blue line. So a planet should lie along that line only, otherwise it doesn't work. Whereas if you account for the effect of the disk mass now, that area kind of broadens, so you get this entire white region. So any planet in the white region can actually explain the observations if you account for the disk mass. And there's also a niche feature mathematically that, for a given curve, these are the values of the disk masses and Earth masses. For all of these curves actually asymptote to the massless disk scenario as you go to smaller, say, major axis of the planet. And when I first saw this, then I questioned whether the discovery of beta peak could actually just be a coincidence, and maybe beta peak was lying somewhere here. And so we thought it's actually it matches the predictions of massless disk models, but perhaps not. And I think the answer is not. I think it was a coincidence. Another way of saying this would be this figure, where I'm showing now for beta peak. I'm showing the time it takes for beta peak B, the discovered planet, to produce a warp at the observed location in its debris disk, as a function of disk mass, okay? And what you can see is that, if the disk is massless, then you can produce the warp within 5 or so million years. But if you account for disk mass, up to 100-ish Earth masses, it doesn't actually make a difference to what you should have predicted if you had assumed that the disk was not massless, right? So the ignorance of disk mass, I think, for beta peak B didn't really change the results much, and so perhaps we were lucky enough to use the simpler models and actually predict something that exists. There are some other, features that, maybe the time scales don't make sense because the system age is like 20-ish million years. And you can see that if I increase the disk mass even further, up to 1,000 Earth masses, whether that's physical or not, that's another question, then the time scale will grow and be more consistent with the system age that we know of. Right, I think that's all that I wanted to talk about today. Which can be summarized by saying that disk gravity is important in planet-disk interactions. Even if you think that the disk is less massive than the planet, you should not be ignoring that. And for the particular case of inclination dynamics, it has implications to how we explain warps and scale heights, which I didn't discuss. But this also translates to on how we infer planets and what motivates perhaps observers to look for planets in debris disk hosting systems, because the predictions can be different. So yeah, thank you for your attention.
So Antranik, you were focusing on gravitational dynamics, but in reality, when the disk warps, there is much more surface area of the disk illuminated by the star, and that could drive a wind, or either through heating or radiation pressure, and these are non-gravitational effects. Do you expect those to change the picture?
Yeah, definitely. So whatever picture I showed here are compatible with ALMA observations, which trace large millimeter grains, which are not really affected by radiation pressure. But yeah, that's an extra step. You can add radiation pressure and see how those will look in infrared observations.
Thank you for being on time.
Yeah.
Questions? Oh, over there, please. Go ahead.
That sinusoidal structure on the edge of the green in the middle figure,
Yeah.
how do you interpret that? What does that mean?
Well, you want the short or the long answer? I have time.
As you wish.
Yeah, so what's happening in this case is that dynamically there's a secular resonance. Okay, so the model precession rates of the planet and some of the planetesimals actually in this region match. So you get a secular inclination resonance, which causes the inclinations of the planetesimals to diverge within my linear model. And so they go to high and high values in inclinations, actually attaining 90 degrees. And this curly tail is basically the path where you have more over density just because of this divergence in the inclinations. And everything after that is kind of like suppressed inclinations, just because that's how the dynamics plays out. And that's why they kind of go and stay flat at larger radii.
I was just wondering what it would look like if you were to observe it.
Yeah. But then I guess I have to account for radiation pressure as well, because like beta peaks JWST shows a tail structure. Whether this has to do anything with that, I cannot say.
It might end up being smoothed out, right?
Yeah.
Any other comments, questions? Looks like everything was clear.
Cool.
Thank you so much.
Thank you.
that's a different talk. This, okay, save. Okay, thanks very much to the organizers. I will explain the general notion of black hole mimickers, why they are well motivated from a theoretical point of view and an experimental point of view. And I will list a few observables that could potentially detect the presence of these objects and distinguish them from conventional black holes in general relativity. So the universe in which we live might contain objects that mimic black holes. And the definition of a black hole mimicker is a star-like object with compactness or mass to radius ratio that is comparable to the compactness of a black hole. In particular, it means that the space-time geometry outside this star-like object is to a very good approximation the black hole exterior geometry. And waves propagating from far away from the star to the region near the star would experience high gravitational redshift. The second feature of black hole mimickers is that they lack an event horizon. And the third feature is that they lack a singularity. These last two features could be construed as an advantage relative to the conventional general relativity black hole. In the context of general relativity with a black hole picture, the prediction for the strength of tidal forces applied on infilling observers is infinite at the center of the black hole, whereas for the star-like objects, all physical observables, including the strength of tidal forces, would be finite. The second theoretical advantage of black hole mimickers is their lack of an event horizon. So in principle, all of the physical information about the object is accessible to the outside observer, even though in practice it may be hard to extract. And in particular, Hawking's information paradox from 1975, namely the contradiction between a calculation of the state of radiation emitted from black holes and the principle of quantum unitary evolution, such a contradiction does not arise in the context of black hole mimickers because of their lack of an event horizon. In the next slide, I want to motivate a string theory approach to the construction of theoretical black hole mimickers. And I will also mention a disadvantage of this approach. And so I should start by saying that both general relativity coupled to matter fields and string theory in its low energy limit contain both solutions with horizons and other solutions in the absence of horizons. In the latter category of horizon-free solutions, some mimic black holes in the sense that their compactness is comparable to the compactness of a black hole. However, the advantages of a string theory approach in black hole physics in general is that in certain cases of black holes that are qualitatively similar to the extremal Reisner-Nordstrom black hole, the thermodynamic entropy formula of these black holes, which is given in terms of the area of the event horizon divided by 4G Newton, admits a state counting interpretation as the logarithm of the number of states of string theory. And similarly, the quantity of the decay rate that characterizes evaporating black holes was explained from a microscopic point of view in certain examples of string theoretic systems. And this capturing of microscopic elements of black holes is something that, to my knowledge, is unique to a string theory framework and has not been reproduced in other quantum gravity candidate theories. The disadvantage of this approach is that one is typically considering phenomenologically irrelevant configurations. But in the last slide, I will show you that we made some step towards something more phenomenologically relevant. So in the last slide, I want to explain in general terms works with Martinek on the construction of black hole mimickers in the context of string theory using an approach of performing ensemble averages over different black hole mimicker solutions. So we have been considering supersymmetric systems in which a simplification to the Einstein's equations occurs. And the simplification is that the Einstein's equations reduce to a set of linear differential equations. And with linear structure, one can superpose different equations or average the equations so as to obtain an averaged solution. And the advantage of this approach is that instead of constructing some complicated solution that represents a black hole mimicker, the product of the calculations is a simple spherically symmetric black hole mimicker. And we have done this in systems with varying degrees of supersymmetry, the latter of which is this 4 supercharges example, is the first spherically symmetric black hole mimicker with respect to the black hole solution considered by Strominger and Waffe from your university, who provided the first state counting interpretation of the entropy of this black hole, which was a big achievement of string theory. In the future, I want to perform ensemble averages of less supersymmetric systems and systems in the absence of any charges, and eventually produce a black hole mimicker in the context of string theory with respect to the Kerr black hole. I want to predict observables such as love numbers, the properties of the photon ring, the spectrum of quasi-normal modes, and the full profile of gravitational waves emitted due to the collision of black hole mimickers in a string theory context. If nature is kind to us, there would be slight deviations between the prediction coming from GR and 2 black holes colliding versus the black hole mimickers. And if such deviations exist, we will be able to rule out one of these models for the supermassive compact objects that exist in the universe. So, thanks for listening.
Thank you so much, Yoav, and thank you for not trying to display some of the equations you are solving. But as you well know, the Large Hadron Collider didn't find supersymmetry in the natural parameter space. So my question to you is...
that's why I want to approach 0 over 30%.
My question is, are you suggesting that it might be possible to rule out string theory by observations?
Yes. Well, one way to rule string theory is to measure deviations from Lorentz symmetry, for example. But the observations that I'm talking about would not rule out string theory, because string theory also has solutions with event horizons and singularity inside. So this in and of itself would not rule out string theory. I'm interested more in whether it would rule out the mimicker picture or the black hole picture.
Okay, is there a way of ruling out string theory?
Yes, which I previously gave you an example. Let me think about other examples. I know them, but
Well, that would guide observers.
Of course.
But what would be your best bet if we wanted to do astronomical observations? Like, what should we find that will rule out string theory?
One thing that people like to talk about is the existence of quasi-de Sitter geometry surrounding us, which there has been debate in the string theory community of whether we actually produced such solutions. Some think that just the fact of de Sitter spacetime rules out string theory. I think that there is a possibility that string theory admits completely controllable de Sitter solutions. And yeah, but I can maybe in private tell you more.
No, because I asked this question Kumron Vafa, and he said that string theory must be right. And so I'm a little bit frustrated that we astronomers cannot really rule out string theory because the string theories do not give us a hook. You know, they. But yeah, anyway, please, questions.
Yes.
So I didn't fully understand. Is it the case that if your universe is from a specific place in the string landscape, you either have black holes with singularities or you have mimickers, or can you
No,
have both?
I would claim that there are only mimickers because of the lack of information paradox and singularity in them. There might be other routes to the resolution of the black hole singularity while preserving the horizon. I don't know, however, how to resolve the information paradox in this context. This seems like the simplest solutions to these problems of positing that there are mimickers instead of the actual GR black hole.
There was another question, please.
Yes. So the Vafa and Strominger paper was to find microstates that can be interpreted to resolve the entropy paradox.
Yes.
So when you say at the end that you find a solution that mimics that, in your case you don't have the information paradox because you don't have it.
Exactly.
So what do you mean exactly that you find a solution that mimics one of the
I mean a solution that is spherically symmetric like the spherically symmetric black hole solution. A solution with high gravitational redshift, with high redshift mimics infinite redshift at the event horizon. And in these extremal solutions, there is a long throat in the geometry, similarly to the long throat in the extremal Reisner-Nordstrom black hole. In our case, we also have long throat. And asymptotically far away from the star, it's the same exterior black hole geometry. So these are the common features.
So one way to find out is to go into it.
Exactly. Yeah.
Would you take a trip into
At the end of my life.
Well, that will show how much you believe your theory. If you can come back to us with a report, then it would mean that you were correct. If not, then you deserve, I guess. Let's thank Yoav again.
All right, can you hear me well? All right, so I'll be talking about something called interacting supernovae and then how we can uniformly characterize. Whoa. What's working? Okay, there you go. So this is my first slide, and so I'll be talking about this interacting type 2n supernovae, and then in supernova classification, we use type 2 for hydrogen rich. So you see the emission lines of hydrogen, and then in this case of this interacting supernovae, you see them as narrow emission lines. So if you look at the spectra of these interacting supernovae, then you see these narrow emission lines where the width is like 100 to 1,000 kilometers per second, which is like, much slower than the supernova ejecta itself, which moves roughly 10,000 kilometers per second. So the physical picture that we have for these interacting supernovae is something like this, that where these lines form at the shock interface of the supernova ejector, shocking the surrounding CSM or circumstellar medium or CSM. And then this CSM is formed by the mass loss activities of the progenitor prior to the supernova explosion. And so since the photosphere forms at this shock interface, it's kind of unfortunate that we don't see much of the supernova ejecta itself because it's below the photosphere. But what's interesting about these objects is that the supernova ejecta trace the CSM outward as it expands. So it traces the final stage mass loss history of the progenitor kind of in reverse because it moves inward to outward. So this tracks the mass loss history in reverse. So we can use this to really study the final stage evolution of massive stars, which is pretty constrained from both theoretical and observational perspectives. So this is why these objects are interesting. And then I'm just plotting a previous sample study from PTF, Palma Transient Facility. And then, it's plotting all the interacting supernova, their light curves in this plot. And then, as you see, it's kind of a mess, right? Like, it's really heterogeneous class where the magnitude spans roughly 5 magnitudes or 100 times in flux. And then the time scales are also really various, like tens of days. And then, so this heterogeneity maybe reflects the diversity in the progenitor populations and or CSM properties of this interacting supernovae. But the sample size back then is roughly 40. So the big question here is, does this really span the whole population of these interacting supernovae? So this is the motivation for our study, that now we have lots of these interacting supernovae publicly classified. And then for those, we can get the photometry from the public transient surveys like ZTF, Atlas, and Gaia. So what you can do is that you can get the photometry from these public transient surveys, and then you plot them in the flux space, and then you can do the 2D Gaussian process, both in time and wavelengths, so that you can get the SED information at any epoch. And then by doing so, you can do the uniform measurements. Let's say what I'm plotting here is the flux in the observed frame, and then the flux in the rest frame. But really simple measurements you can do is just find the peak flux here, and then measure the time scale on the rise. Let's say, how long does it take from the 50% flux to the peak? And then how long it takes from the peak to the 50% flux in decline. These really simple measurements in the peak flux and then the time scales. So this way, we can plot the sample distribution here, where y-axis is the peak magnitude in the R band, and then the x-axis is the redshift. So this is just showing the sample distribution, and then these dotted curves show the limiting magnitudes of the survey. So our sample dominantly comes from ZTF and Atlas, so they are about 20.5, which is the limiting magnitude of these surveys. And then some of these high redshift events come from Pan-STARRS, which went much deeper. But what I want to emphasize here is that in the previous messy light curve plots, I plot the PTF sample, which is 30 or so. But our sample in this plot, what I call as nullo, as type 2n, is 400, more than 400. So this is an order of magnitude increase in the sample size. And so now I call this as the largest sample study of these interacting supernovae. And if you plot all the light curves, again, it's kind of messy. They span a wide range in the, in this case, I'm plotting the optical luminosity light curves. They span a wide range in the peak luminosity, also in the time scales. But you kind of start to see the two populations, where one is faint and fast, and then the other is more luminous and longer duration. So you see over densities of these. So there might be two populations within this heterogeneous class of interacting supernovae. And so you can plot the measured properties here. So that's what I'm plotting here. On the y-axis is the peak luminosity. And then the x-axis is the time scale. So 50% from the rise to the peak, plus the time scale from peak to the 50% flux on the decline. So, again, it spans about an order of magnitude on the time scale. and then 2 orders of magnitude in the luminosity, peak luminosity. So again, it's a heterogeneous class, but there is an overall correlation between these luminosity and the time scale, which is a straight line here. But you can do something a bit more fancy. You can rotate the whole sample along the best fit correlation. And then something really interesting shows up. So this is the fit, and then I'm rotating around the median of the peak luminosity and then the time scale. So if you look at the distribution along the x-axis here, you start to see this more like bimodal distribution along the correlation, which you'd not expect from a uniform distribution. So there's something going on. There is some bimodality along the correlation. So this is really exciting. I didn't really expect to see this. And so now this is like my summary plot. So you can now plot the luminosity as the x-axis, and then the radiated energy, which is essentially the luminosity times the time scale. So you combine these, two things together, luminosity and then the time scale, then you can plot the characteristic time scale as the diagonal lines here. So again, these more luminous events have characteristic time scale of 100 days or so, while the less luminous ones have 30 days or 50 days or so. And so, and what's interesting here is that you see the clear bimodality in the radiated energy. So that's interesting. And then you can use this, let's say the median is here. So you can split the sample into 2 using this median value. And then what I'm plotting here are the light curves of these 2 populations split by this median radiated energy. So what I want to emphasize here is you can make the light curve templates or the median light curves of each class or each group, where I'm plotting these solid lines at the medians, and then the spreads are 1 and 2 sigmas. And then they only overlap at the 2 sigma level. So this is a really clear separation within this heterogeneous class. So the bimodality clearly separates the light curve morphology into 2 groups, which I call luminous slow, and then the other as faint fast. So this is the take-home message that these interacting supernovae are heterogeneous, yet they show bimodal distribution. So this might reflect the fact that there are 2 major progenitor or cells information pathways. So we are trying to understand what's really causing this strong bimodality. Maybe it's the progenitor system where maybe one class represents more less massive stars, and then the other corresponds to more massive stars. Or maybe there are differences in the distribution of the circumstellar medium. So we don't really have a clear answer yet. So that's coming in. This is the first paper of the series. So that's coming up in paper 4 or something where we do the modeling. But I just want to advertise our project in the current and then the coming HST cycles, where we are doing the host galaxy studies using the sample study of the host galaxies of these interacting supernovae. And then we want to do this in the rest frame UV so that we can track the star formation rate at the local environment of these supernovae. So this was done in other types of supernovae. One is showing was done by former undergrad here, Brian Shu, who did this kind of study for something called superluminous supernovae, which the name suggests, mysteriously luminous supernovae. And then what you can do for each of these images is that you find the brightest UV pixel within the image, within the host galaxy, and then you compare that value to the UV flux at the supernova location. So which is shown as the x-axis here as the fraction flux, and then this is just showing the distribution. So this kind of traces the star formation rate within the host galaxy. And then you can now compare other classes of transients like superluminous supernovae, long gamma ray bursts, core collapse supernovae, type 1bc, or anything. But this hasn't really been done for these interacting type 2n supernovae, so that's the goal of this project. And then you can also plot the offset from the host nucleus, or like the center of the host galaxy. And then this kind of tracks the clustering within the host galaxy. And then you can also compare this distribution with the other transients. So we got 222 snapshot orbits across 2 cycles. So by doing this, I'm just plotting the distribution as a redshift and then the peak absolute magnitude compared with the archival sample, which already exists. And then these are roughly 26 of these interacting supernovae. But with our proposal, we can increase the sample size by 7 times. So it will be interesting to see whether there's any correlation between the host galaxy properties with these properties that I showed for these interacting supernovae, and then whether they track the star formation rate or clustering within the host galaxy. And then this will give us a clear idea on what's really going on within the population. So thank you so much.
We don't have a lot of time because we are over the time limit, but could it also be just a viewing angle distinction between the 2 classes that you found? In other words, if you have some torus of hydrogen, if you look, it's just like active galactic nuclei. If you look from above or from the side, you get different kind of AGN.
Yeah, that's an interesting, so we don't really know the CSM distribution, whether it's spherical or maybe a disc-like, as you mentioned. So that could correspond to some, diversity within the population. But I think by the fact that we see narrow emission lines in the spectra tells you there is a quite efficient conversion from the supernova exposure kinetic energy to the radiation at the shock interface. So if you translate, that efficiency is roughly 10%. So if you if you translate this radiated energy to the kinetic energy of the supernova ejecta, this roughly corresponds to 10 to 49 or so in the radiated energy. So maybe the explosion energy is 10 to 50 arcs, while for the luminous ones, maybe radiated energy is 3 times 10 to 50. So maybe the kinetic energy is more above 10 to 50 arcs, which is the vanilla exposure energy for supernovae. So I think there's also something going on within the intrinsic property of the supernova on top of the distribution in the CSM.
So it's a different engine you're saying?
Yeah,
okay.
probably.
We need to close, so
Yeah.
let's thank